Welcome to this explainer. Today we're diving into a genuinely mind-bending mystery about the physical world. You know, we grow up thinking math and science are these realms of absolute, unquestionable precision. It's easy to assume that if you just get a fancy enough tool, like a multi-million-dollar atomic clock measuring the exact vibration of a cesium atom, you can perfectly measure the length, weight, or time of literally anything. But here's the secret that kind of shatters that whole illusion. A perfectly precise measurement? It doesn't actually exist in the physical world. Every single time you measure something, no matter how advanced your technology is, you are hitting a hidden physical limit. So we're going to explore exactly why that is and how scientists use a really clever system to handle this universal imperfection.
Okay, let's dive into this by drawing a line in the sand between counting and measuring. There is a massive difference. Think about a glass jar full of candies. You can dump those out and count them. 1, 2, 3, 4. You can know the exact, indisputable number of candies, right? There's no such thing as a fraction of a candy in your count. It's a perfectly exact integer. But measuring a person's height, that is fundamentally different. It's continuous. Nobody is exactly 5 feet or exactly 6 feet. Depending on your tape measure, the angle you look at it, or even the time of day, that measurement always has a little fuzziness to it. You just can't perfectly capture continuous physical properties with absolute certainty.
So what does this all mean? Well, that fuzziness actually has a formal name in science. It's called uncertainty. And this is absolutely crucial. In physics, uncertainty doesn't mean you messed up. It doesn't mean you spilled coffee on your lab notes or you're just bad at measuring things. It means there's an inevitable limit to accuracy in literally any measurement, purely because of the physical limits of the instrument itself. Whether you're using a cheap plastic ruler from a craft store or a billion-dollar laser in a quantum lab, every single tool has a smallest division. It has a minimum threshold of what it can detect, and that physical cap introduces uncertainty into our data.
To see how this plays out in daily life, just look at the tools lying around your house right now. Take a standard ruler. It's got those tiny empty spaces between the millimeter marks. If an object's edge lands in the empty space between the 10.3 and 10.4 centimeter marks, the ruler physically cannot tell you exactly where it is. You, the human, have to guess. Or think about a digital scale in your bathroom or kitchen. Have you ever stepped on one and watched that final decimal point just flicker back and forth between a 4 and a 5? That fluctuation isn't a glitch. It is the instrument actively encountering its own limit of precision. It's showing you its uncertainty in real time.
Now, since we can't ever completely eliminate this uncertainty, scientists have to actively work around it. One of the best ways to do this is to never, ever trust a single measurement. Like, if you try using a stopwatch to time a fast event like the swing of a simple pendulum, your own human reaction time adds a ton of uncertainty. You're going to click the button too early or too late for sure. Instead, you measure the total time for 30 swings. Then, you divide that huge total time by 30. By taking multiple readings and averaging them out, you smooth over those tiny errors and significantly drop the overall uncertainty of that single swing's time.
Let's look at a classic student lab dilemma to see exactly where this uncertainty lives in a number. Imagine two students looking at the exact same physical rod resting against a standard ruler. The edge of the rod clearly passes the 4 centimeter mark, and it passes the halfway point, but it lands right in the blank space between the 6th and 7th millimeter lines. Student A squints at it and says, "I estimate the rod is 4.6 centimeters." Student B looks at the exact same rod from a slightly different angle and goes, "No way, I estimate it's 4.7 centimeters. So who's right?" Actually, they both are. They're just doing their best with a limited tool.
What's really fascinating here is how we break down their disagreement. Notice what they don't disagree on. They completely agree on the 4. That first digit is a reliably known digit. The ruler gives us that 4 absolutely. But that final digit, the 6 or the 7, is mathematically doubtful. Science literally calls this a probability of error, because that final number is based purely on human estimation between the visible lines of the instrument. In any measurement you ever take, your final digit will always be this doubtful estimated number.
And this brilliantly illustrates the concept of significant figures. I know, a lot of students think significant figures are just frustrating, arbitrary math rules designed to make test questions harder. But they really aren't. Significant figures are actually the universal scientific language of honesty. They're how scientists tell each other exactly how good their tools are. By definition, significant figures are all the accurately known digits in a measurement, plus that first doubtful digit. When you record a measurement using proper significant figures, you are making a promise. You're saying, "I know these first numbers for a fact, and this last number is my best educated guess based on the limit of my tool."
So how do we know which digits actually count as significant? Well, numbers 1 through 9 always count. The real tricky part is the zeros. Just think of zeros in 3 ways. First, are they trapped between 2 regular numbers? Yes, they count. If a measurement is 5.06 meters, that 0 represents a real measured empty space, so 3 significant figures. What if they're leading the pack on the far left? No, those are just placeholders telling us where the decimal point lives. They don't represent the tool's precision. So 0.0034 meters only has 2 significant figures. But what if they are tucked at the very end on the right side of a decimal? Yes. If a scientist writes 2.40 millimeters, they are intentionally writing that 0 to tell you, my tool was precise enough to measure this exact spot. That gives us 3 significant figures.
Now, there is one incredibly helpful exception to these rules, and it comes up a ton when scientists are dealing with massive distances like the gap between galaxies or tiny measurements like the width of an atom. When numbers get that extreme, we use scientific notation. The rule here is wonderfully simple. Only the digits recorded before the multiplier, the times 10 to the power of whatever, are considered significant. So if you see an expression like 3.50 times 10 to the power of n, you let the math handle the massive scale, and you let the front numbers handle the precision. You just look at the 3.50. Based on our previous rules, that gives us exactly 3 significant figures.
All right, we've gone over the theory, but let's see how this builds into real practice. I'm going to give you a rapid-fire quiz to test your new knowledge. Take the measurement 12.5 centimeters. Take a second. Apply the rules we just discussed. How many significant figures are in this measurement?
If you said 3, you nailed it. Let's break down exactly why. We have the digits 1, 2, and 5. There are no zeros to complicate things here. All non-zero digits are always significant. The 1 and the 2 represent our reliably known digits, given to us clearly by the measuring instrument. And that 5 at the very end? That is our one doubtful digit. It's the scientist's best estimate at the absolute edge of the tool's capability. So, 3 digits total that communicate the precision of this measurement.
Okay, let's try one more to really make sure this is locked in. I'm going to throw a bit of a curveball at you this time, using the rule for zeros. Take this measurement, 0.000125 kilometers. Think back to the rules we looked at a few moments ago. What happens when zeros are located to the left side of our actual measured numbers? How many significant figures do we have here?
The answer is 3 again. Did I trick you? Let's aggressively remind ourselves of that crucial rule. Leading zeros do not count towards the scientific precision of the instrument. Those zeros are completely necessary for math. They tell us that this is a very, very small fraction of a kilometer, but they don't tell us how good the ruler was. Only the 1, the 2, and that estimated 5 at the end represent the actual physical measurement taken by the scientist. As we wrap up this explainer, I want to leave you with a thought that really stretches the boundaries of how we view reality. We've established that uncertainty isn't a human failure, right? It is a fundamental property of interacting with the physical world. If every measuring tool in existence, from a cheap wooden ruler to an atomic clock, has a physical limit, is it ever